Thank you all, and good afternoon. I hope you all enjoy your lunch, and there's lots of people here, so please cram in a little bit to the back. And I hope to make this talk entertaining enough so nobody falls asleep. So for those of you who don't know, PyMC3 is a Bayesian computation package built on top of Variational, which is a tensor computation library. And so just a little bit of plug-in for those of you who don't know. PyMC3 is written in Python, and it has, we can see the state-of-the-art inference engine, NUTS, and a variational inference. And it is under active development, and it has a really awesome community. And for me personally, if you ask me why do I like to use PyMC3, instead of all these other libraries out there on the free to use, I often think that PyMC3 gives us a way that is really easy to interact with different components of your model. And I hope today that from my presentation, you can get to see a little bit about, okay, how can I get the likelihood from different components, and how can I, when I build a model, how can I check different parts of the model to make sure that I'm doing things correctly. So for me personally, I've been a developer for PyMC3 for the past year or so. And currently, I'm mostly maintaining a community of the PyMC3 on Discord. And I highly encourage you to check it out of the discourse. We not only discuss specific problem of using PyMC3, but also if you have, for example, in a journal question about, okay, I have this problem, I have this setup, how can I use how can I use Bayesian statistics in general? You can post a question on the discourse, and usually I would try to just do a quick reply of, okay, here are some previous discussion on this topic. You can check it out and hopefully to kick up the discussion a little bit. So I actually, I'm from a psychology background. So I study psychology in my undergrad and PhD. And I always do this frequency statistics. So I actually teach Bayesian statistics myself by using PyMC3. And some of the haunting question of my quest of learning to be a Bayesian is quite challenging, and some of the questions, for example, how do we sample from the, why do we sample from posterior, and how can we do that? And more specifically, I used to be always kind of confused of, okay, why do reparameterization works? So, for example, a famous case is, okay, you have you have some samples from a normal distributions, and you can sample it directly from a Gaussian with the parameter of mu and sigma, or you can sample from a Gaussian with zero means and the sigma is a 1, and then do a linear transformations. So this is famously known as center or non-center parameterization of your model. And sometimes one works better than the other, but why is that? Because if we say that, okay, this two-way gives you the same kind of model, then why would it work that one way works better with the other? And I think all these questions can be a bit better understand by know a little bit more of what exactly is a likelihood functions. So today, I will first kind of go through a little bit of the basis of, okay, what is a probability? What is probability, density, or mass functions, and how does it link to a likelihood functions? And then a bit more practical of, okay, if I'm building these models in PyMC3, how does it compute the likelihood, and how can you extract the likelihood of the model and of different components? So in our daily life of doing data science or analyzing data, we are dealing with a specific thing called random variables. We might not define it mathematically all the times, but basically it's a numerical measurement of some outcomes of a probability experiment. Those value is determined by chance. So formally, it's a function that maps the outcome to the of some unpredictable process to a numerical quantity. So this is all really mathy. So what does it actually mean? So a random variable describes kind of a summary of some process. For example, thinking of flipping a coin 3 times, and we can observe head and tails each time we flipped it. So at the end of this series of this specific experiment, we can have different outcomes. For example, we see the first 2 being heads, and then the third one being the tail. And if we do a summary of what we observe, we say, okay, we observe the number of heads being 2 times. But actually, as you can see here, there are 3 different paths we can get to this event. So a random variable is this number of heads we observe, so 3, 2, or 1, or 0. But the process is describing is some kinds of random procedure or random experiments. And when we are dealing with a random variable, usually we are dealing with, it associated with some kind of probability distributions. So probability distributions is specify the probability that its value fall into a given intervals. For example, in this case, if we are rolling 2 dice, we can observe a random variable takes the value between 2 and 12, and this random variable will be the sum of the face value of the two dice. So the experiment itself is rolling dice, and the event you observe is different numbers that comes out in the 2 dice, and the random variable is the summary, the sum of these 2 numbers. So regardless of how specifically these 2 dice the number is, what we care about is the sum of the 2. And so this is an example of a discrete random variable, and we also deal with a random variable on a continuous. It can take a continuous values. And in this case, maybe a point value is not that much of not that much of meaning anymore. But what's more important is the value of the given interval. So these are all covered on just a quick introduction. Is on Wikipedia, and all this theory is based on formally defined of some kind of mathematical foundations. Of course, I will not go into detail of it today, but there's this recent blog post by Michael Bittencourt. I highly encourage you all to read it. It gives you some formal language of how you can think of mappings, what is defined as a random variable, and these things. And in practice, we usually are dealing with a very limited specific subclass of distributions. So, for example, here are two different cases, and they mostly are coming from, for example, exponential family, for example, Gaussian, or a Poisson, which gives us really nice properties. So, okay, let's think of a more specific case, still a coin flip examples. So we are not talking about Bayesian if we're not flipping a coin. So say now, okay, Alice flip a coin for 5 times and observe 3 outcome is heads. And here, the random variables would be the number of heads that it observed. Of course, you can define differently. Say, okay, you can say it's the number of tails. That's also a random variable. But the underlying kind of physical experiment that is summarizing is still the same. And also, it comes also with some specific kind of presets of the experiment. For example, actually, you can get 2 different settings. For example, the first setting is that you flip to a total number of 5 times and then record the output. And usually, it will associate with a binomial distribution that describes all the probability of observing different number of heads. Or you can have a different setting that, okay, I actually flip the coins until I observe 3 comes out as heads. And now it can be summarized as a different a different distribution as a negative binomial. So again, the underlying physical random experiment is still the same, but the random variable in these 2 cases are actually different. So, okay, let's say that we stick with the first settings, and we are dealing with binomial distributions. And usually you see that it's written as such. But you can also, I actually encourage you to think of it different ways. That it takes 3 different possible input to these functions and gives you 1 output of the functions. So the following slides, there will be some demos. You can check it out on these notebooks. Right, so let's start with the probability mass functions of a binomial distribution. So usually we can import it from SciPy, and it gives us a really handy mass functions of the distributions. And usually we define it as such that, okay, assume that we know the number of coin flip, and assume that we know the underlying binomial rate. What is the probability of observing different outcomes? So this is a way to show you that there are, if you in a kind of conventional way, when we are thinking of a probability distribution, we have the latent or the unknown as the binomial rate. So, and if we kind of vary it differently, my apologies, I have a cold, so. So this is to give you some intuitions of, okay, if I change the underlying binomial rate, how does the distribution will change? And this is we normally know as probability distributions. And as for likelihood, we now kind of change the thinking a little bit. Instead of seeing how the outcome changed by the different rate parameters, now the binomial rate is kind of like our unknown. And we change the switch to observe a little bit. So to read this graph, is that you see on the x-axis being the binomial rate parameters, and it takes the value between 0 and 1. And the probability, and the y-axis defines a probability. But this is normally called likelihood functions. The reason of these distinctions is because it doesn't integrate it to 1. So if you compute the area underneath the curve, it does not integrate to 1, so it doesn't count as a probability density functions. But actually, this distinction might be a little bit misleading. As you can see, we are still using the same probability functions from SciPy here. And sometimes I like to think about it as the likelihood function is the function that the parameter is equal to the density, but you index by changing the input to the function. So what does this mean? So let's look at again our for probability distributions or mass functions. Actually, we have 2 parameters. If we are taking this conventional form, there are 2 parameters that are unknown, or it can vary if we are observing some kind of a random outcome. The first one is the number of total coin flip in this case, and the second one is the latent variables of the binomial rate of the coin. And interesting thing to note, kind of like a minor technical detail, is that actually when we are talking about a probability function or probability distributions, or for example a binomial distribution, we are talking about actually a family of binomial distribution. And only when we fix the 2 parameters, now it becomes a specific function. And now this is the interesting part of, okay, what about the likelihood in this under this context? So now we are still have two kind of unknowns. And in this case, we are changing the outcome to see what is the likelihood looks like. And this is still a likelihood functions, but each of the entry or each of the small cell in here is a probability. And what you will observe is that kind of in the bottom, there, it takes the value of 0. It's kind of impossible value, because when you observe, for example, a number of heads is 10, it's impossible that you flip the coins less than 10 times. And so immediately, it kind of gives this constraint, and it changes the surface of how the likelihood functions will look like. And also, it takes two parameters, because we have two kind of latent variable or unknowns. But it's all, we are still dealing with kind of the same SciPy functions, if we are using SciPy here. And we give the inputs to it as, now since these two are unknown, I just vary it randomly, or I just lay out the whole grid of all the possible values. So again, this surface gives us more information of what a likelihood really looks like. And I encourage you, when you are thinking of a likelihood, you should all imagine you are in this kind of space that makes up by different inputs or different coordinates. And also, an interesting thing just to point out is that if you are looking at this space and we are doing maximum likelihood estimation, actually we'll get the maximum likelihood at the edge here, which in this context will be, the maximum likelihood is that we flip the coin for 7 times and we observe the head 7 times. So it's kind of like, sure, this is still a correct answer, but it's a little bit pointless, because it doesn't really capture the shape of the likelihood space. And that's also sometimes of a reason that why we really discourage of when you're thinking of just one point estimation, because it can always be misleading. And probably more naturally, when we are thinking of a distribution or a likelihood functions that takes 2 inputs, we think of like a Gaussian likelihood, which we have unknown, for example, is the mu and the sigma parameters. And it naturally maps out to this kind of a 2-dimensional space that we have 2 different unknowns that we want to find out. So just as a quick recap, we are using the same functions when we are dealing with probability, either probability density functions or likelihood functions. And it might not be really useful when we're making a very clear distinction between the two, because the output we are dealing with is still a probability. And so, now we cover kind of the case. We have 1 observations of this random experiment. But what about if we have multiple observations or repeat measurements or repeat experiments? And it turns out there are ways to combine probabilities with all these formal rules. And as a consequence, there is these 2 famous rules of sum rules and product rules, which also give us naturally the Bayesian theorems. So now let's take a specific case, still with the coin flip. Imagine that we have a new coin flip experiment, which we just flip the coins for 1 time. But we will record the outputs. So the random variable is just head or tails, or 0 and 1s when it maps it to a real number. But we actually repeat this experiment 6 times. And say that we have the binomial rate is 0.7. So by the rules of combining different probability, the probability of observing this exact sequence, we can evaluate it as such. And at the end, we have the probability of observing exactly this sequence. And as you can see, we are just doing a multiplications of each experiment, and at the end arrive at these answers. And we can also use the SciPy function of Bernoulli distribution. And usually in our daily life, we use a log likelihood because it's easier to work with for computers, and we avoid lots of numerical problems when we are computing it. So in this case, we can take the log of each of the outputs, or we can just use directly the log probability. And now, if we define these likelihood functions of observing this sequence by using doing kind of these lambda functions, and we evaluate of all the possible range of values of the binomial rate, we get this kind of functions. So on the left, we have the likelihood functions of observing exactly this sequence. And on the right is the log likelihood functions. So how do we get these functions? How do we get these things with these shapes? Now let's take to look at just the one experiment. And if we observe the coin become outcome with zeros, we have this kind of likelihood. And quite naturally, we can think of it that okay, if the probability being zero, or the binomial, or the coin, or the rate of the coin, the true one being zero, then of course when you flip it, it comes up with zero. So we have a 1 on the far end, and it's just linear decrease. So it means that when you have 0.5, so the coin is fair, then it's half and half. And the same for the occasion of when it comes up with 1. And now, when we are looking at this sequence, we can do updates of, okay, when we have more observations, we can update the likelihood functions. So again, we observe 0 in the first experiment, we observe 0 again in the second experiment. And by the rule of the probability, then we are just multiplying them. So we get if we multiply the first two, we get the third one. So that's the likelihood function of observing consecutively 2 zeros. And we can repeat this procedure. So, okay, again, we observe 0, so we update further. We observe 0 again, we update further, so on and so forth. And which give us this kind of sequence of updating. And by the end, we have this likelihood function with this shape, which it defines for likelihood functions that observing exactly this sequence. And again, this function, we take the binomial rate as the Bernoulli rate as the input on the x-axis, and on the y-axis is probabilities. And you might already observe that if you are familiar with a binomial probability functions, you say, actually, the two has exactly the same shape. It's because the binomial trial is actually kind of a generalization of a Bernoulli experiments. And in this case, it's just that since we don't, in a binomial trial, we don't care about the sequence of the head and tails. So actually, the actual numbers here are different. So you can see in the bottom is that the numbers are higher, looking at the y-axis, the number are higher than in a Bernoulli likelihood, but the shape is still the same. And now say that we are repeating a binomial experiment with this sequence, we can now apply it the same as we previously see. And just as a reminder, the operation we are doing here is that we observe the first trial of the experiment, second trial of the experiment, and then we combine the two using multiplications, and we just continuing these procedures. So again, a few things just to as a note is that okay, the order of the sequence kind of doesn't matter. And at the end, you observe these shapes. Oops. So now let's take an example of a Gaussian likelihood. And here is the first two trials. And if by the same procedures, we are multiplying them, and it gives us this kind of updating of when we have series of Gaussian observations. So a few things to note here is that when we are talking about the likelihood of just one observations, actually it gives no information of the sigma, because of course when you have one output, we don't know what the sigma would be, so we don't know how randomly it will vary. But as soon as you have two observations, you can infer the parameters, or it gives these shapes of how the sigma will look like. So it has these peaks here at the end, where it gives us more information of, okay, how is the other parameters will look like. So what about priors? Because now we know about likelihoods. And what about if we want to incorporate priors? So say that we specify some priors for the mean and the standard deviation for these Gaussian examples. And when we are thinking of the operations in these two dimensions, we are actually broadcasting this probability into two dimensions. So here you see the first one being the mean parameter, and the second one's being the sigma. Again, the axis here is not very meaningful, so just try to ignore it. And when you combine the two, it gives us the third shape. So now let's say that we have this prior, and we have now our same observations. And we see that it changed the shapes a little bit when we are doing these updates. And we can compare them with what we originally see. And you see that, quite interestingly, only the first one is kind of like giving it a lot of information. And as soon as you have more trials, the prior information kind of quickly wash out. But it's not always the case because you can have very few informations of informing you how the likelihood looks like. And in those cases, of course, your prior becomes much more important. So now let's go to PyMC3 and with some actual examples. So go back to the coin flip examples with a binomial trials. But it's a little bit kind of unconventional is that let's say that we also don't know about what is the total number of coin flip, and we just give it a uniform between 0 and 25. And the observation here is 7. And when you define these models, you can check what is the inputs to the likelihood of these models by checking the test points. So here the test point is, because we have two unknowns, we have the test point is also takes kind of, you need to specify the coordinate of these two unknowns. And you can also get the likelihood of different components. So we have the components for the model likelihood, and we can also have we have the likelihood function for the model likelihood and also for the component likelihood. And for these likelihood functions that it's called loose point functions because it takes a point or a dictionary as input. And here, what I'm doing here is that I evaluate the likelihood functions for both the model likelihood and a component likelihood. So for here, you can see that the component likelihood is kind of, it takes no limits from 0 to whatever numbers. But when you're looking at the model likelihood, it has this cutoff at 25. It means that the prior information is kind of kicking in. It restricts how large this space can be, so it can only go to 25. And how PyMC3 uses Variational in this case is that when you define a PyMC model, we build up this graph of these functions that it takes all some inputs and it returns the output. So formally speaking, in this example, it takes a real number and also integers, and it outcomes another real numbers. And it has two kind of free random variables as we defined it. And these two free random variables if you check just one of them, it has two kind of likelihood functions. But don't be kind of confused between the two, because one is a kind of a property of a distribution or of the distribution or the underlying distribution, and the other one called log pt, which is a tensor that is kind of like the actual things that we're interested in. So, for example, if you're defining some random variable that is a size 10 arid, actually the log p is still, if you don't specify the size, the log p is still only defined on a scalar, but the log pt in this case is evaluated on this size 10 array. And then in PyMC3, we collect all the component likelihood, and then we do the sum to get the kind of this model likelihood. So when you have constraints from the prior or you have information from the prior, here is where it kicks in the model likelihood. So let's just quickly go through two examples. The first one being a general linear models. And you can check it out in these notebooks called regression with a twist, is kind of. So the first way, when you define a regression, so with the data as this, when we first define a regression, we usually model it as this. So we have the two unknown parameters, one both with a normal prior, and with the observations as also following a Gaussian distribution. So this is kind of like a conventional way you should define your model. But actually, it's equivalent if you define your model as such. It's just internally what PyMC3 does is that it will first collect the log likelihood for the first 3 parameter. And then for the second parameters. And then for the third or actual observed random variables. And the potential is like kind of like calculating the log p, and then it collects it in the model log likelihood. And actually, when we are thinking of this in the likelihood space, you can do all kinds of crazy stuff with it. For example, you can do it with like this little bit twist. Is that okay? Instead of defining that my observation is following a Gaussian distributions, actually my observation subtracting a linear prediction is following a Gaussian with a zero mean. So it's kind of like more to the frequencistic sense. But of course, this is not really encouraged you to do. It's just to give you a sense of if you are thinking of a space of a likelihood functions, actually these two are equivalent. But be careful is that actually it's not equivalent if you do the first case. When we actually divide in the 3 parameter of standard deviations and then give it a Gaussian of a 0, 1 Gaussian of likelihood. It's because that actually when we are doing things like this, we implicitly change explicitly change the volume of the likelihood space. And we need to account for the volume change in the transformations. So when we have transformation, it's just a fine transformation, just switching it around, the volume stays the same. And actually, this is what SciPy define when you have a scale, a location scale distributions. And there's a more information of a more complex example with a news funnel that it deals with, it shows you that, okay, if you actually account for the volume change, you have the 2 identical models. And I'm running out of time. So just very quickly, as a last example, is thinking of a mixture model likelihood. So a mixture model is really difficult to fit because we have this problem of label switching. So for example, if we sample, sometimes we see that the labels switch back and forth. Here is between different traits. And so how do we deal with these problems? And usually there's 2 ways. So let's take a concrete example of, okay, this is the observed data. with the normal mixture distribution, with the mean being -1 and 2, and the weight being 0.3 and 0.7. And if we kind of map out what the likelihood space looks like, it looks something like this. So why do we see label switching? It's because when, as a sampler, when it tries to map out this whole space, actually it needs to jump out between these two local maxima. So which means when you have difficulty jumping from one to the other, you have a problem of exploring the space properly. And usually there's two ways to kind of, many different treatments for this. One of the most kind of the ones that works the best is order transformations. And I used to be really confused. Okay, the order transformation kind of gives it the order, but what about if I just sorted the variable? Because if I sorted the variable with no constraints, then the outcome is always one larger than the other, and the trace seems to be fine. But actually, it's not. If you look at the space of the likelihood functions, actually there's still these two local maxima, which means as a sampler that's trying to map this space, if you still have problems of exploring the whole space. And just as a comparison, what it changed is that it kind of now mirror the two space. So when you're looking the parameter after you do the transformation of sort the two values, it's kind of you kind of think, there's no problem, but actually there still is from the sampler point of view, because the sampler is only kind of this little torch that only sees a little area in the parameter space. So, and as a more formal treatment, you should either use the potential, which gives it the order, or use the order transformations. And just quickly to show you is that now it actually modified the space, and you have a different parameter. The parameter space is different. So as a recap is that there are many ways to write down your model, and reparameterization is more or less always change the model likelihood. So if you evaluate the model likelihood with one parameterization than the other, you should expect the likelihood output change, because otherwise there's no point of writing down your model differently. And so here are a few pointers. For example, make sure it's correct. Good parameterization should be easy to understand. And I will just really quickly skip through here. Just focusing on the last point is that when we're building models, we are setting up some kind of space. So it comes into a concept of coordinate space, which you can see more in these examples. And also, it's interesting also to think about regularization, because you are also modified in a space and how it links to Bayesian computations. And also, this good way to check your model by looking just at the slice of your likelihood function, because now in a slice, you can plot it. And here is one of the recent discussion of how to use this technique to check your models. And lastly, just some thoughts that I encourage you to have a read afterward. And thank you very much for your attention.
Let's thank our speaker, and we have time for 2 questions. Do we have questions?
So hello, I have a question. Like, as Fiano is being discontinued, what is the idea for PyMC3 to use that? So to switch it to some different system, or use some legacy version, or is it a different approach?
Yes, actually, we have a recent blog post on this, so you can check it out on Medium. Basically, the plan is for PyMC4, we'll be partnering with TensorFlow and TensorFlow Probability to build a new interface on top of TensorFlow. And for PyMC3, actually, we are still developing. And most likely is that we will have some resource to kind of take over the maintenance of Fiano, or we have kind of a local port of Fiano just to make sure that it still continues to work under PyMC3. And maybe in a year or two, we will have a stable release of PyMC3 with Fianos that you can expect it to still works for the couple of years.
So thank you.
Yeah.
I think no more questions because people need to switch.
Then let's thanks again our speaker.